Recording already.
All right, I think we should be all set here. Let's finish this up. I looked at all chapter 6. I think you can get that done. The deadline for that is due tonight. The deadline for chapter 7 is Friday night. I think we're all right. Then the quiz is with it Friday night, right? So answer questions on that. Print out. If you haven't printed out the last chapters 8, 9, do that because we should be starting that very soon, if not just a dabble in it today. Okay, for quiz questions, first we got 18 here. All right, so 18. This ends in, I'm just looking at the ending. This ends in 3s1. 3s1, you can do any table, your blank table would work. This is 1s1, 2s1, 3s1. All I did was look at the ending for 3s1. And this element right here that ends in 3s1 should be sodium, right? If we look at the ending electron configuration notation, what it ends in, and you could write the whole thing down. But all we care about is where it ends. That would tell you where you're at on the periodic table. All right, then we got 20, 18, 21. How many valence electrons would be for this element? Now, for valence electrons, all we care about is the farthest out, highest level S and or P's. So this that I'm going to highlight in yellow, we call the core electrons. But we got to level 4. This is my valence electron right there. Level 4, this has 1 valence electron. Now, question. I don't remember in the previous, do we have this on your blank periodic table? The answer to that is no. All right. So let's do that. Let's go to your blank table here because we're going to do that today anyway. So let's fill that in right now. Your valence electrons, because we're going to need this all the time for the next chapter. Your valence electrons, everything in group 1 has 1 valence electron. So this is page 20 on our blank table. Because this, for example, is 2p6. Once you go to level 3, these are core electrons. 3s1 has 1 valence electron. 3s2 has 2 valence electrons. So my valence electrons right here matches this group number right here. So everything in group 1 is going to have 1 valence electron. Everything in group 2 is going to have 2 valence electrons. Some textbooks, some people will include unfilled Ds. I've been told to stay away from that by my boss, so that's what I'm going to do. But when I get over here to group 13, how many valence electrons for every element in group 13? Well, if we took this, it would be 3s2 and 3p1. This would be 3 valence electrons, right? 3 valence electrons, the 3s2 and the 3p1. Everything in group 14 right here is going to have how many valence electrons? 4, because it would be 3s2, 3p2. Everything in group 5 is going to have 5 valence electrons, because it would be 3s2. If I take this element right here, it'd be 3s2, 3p3 for a total of 5, 6, 7, and 8 valence electrons. So when we get over here, it's the ones place. We're going to be using this all the time. The next chapters, it's the ones place right here matches our valence electrons. helium would have 2 valence electrons, but after helium, it's just the ones place should match your valence electrons. Okay, so that was 21, 23. So this element right here, this is my core electrons, not my valence electrons, because once I get to level 3, these are valence electrons. Now, what does this end in? This ends in 3s2, 3p2. Right? The last things we would write down, in fact, I'm only writing down my valence electrons. And we could write this down using our group 18 noble gas configuration. We would do neon in brackets because this portion right here is neon. So if it ends in 3s2, 3p2, or 3p2, first of all, it ends in p2. It has to be in this column. It has to be in group 14, right? And 3p2 would be this one right here. It ends in 3p2, or it ends in 2p, 3p. Remember, this is p1, p2, p3, p4, p5, p6, right? So if it ends at 3p2, it's right here. And 23, 36, 36. All right, 36 is a review question. Let's see what we got. Nitroglycerin decomposes violently according to the unbalanced equation below. What mass of nitrogen gas is produced? Okay, so let me. All right, so this is we've got 0.3 moles here. All right, balancing this baby. How ugly is balancing this thing? What do we start here? We could start with, carbon, nitrogen. Let's do nitrogen here. So there's 3 nitrogen right here. There's 2 nitrogen here. So least common multiple there is going to be 6. So for sure, I have no idea if this is going to work. A 2 and a 3 for my nitrogen. Who's got this balance? Does this work just like this? No, this doesn't work like this. Am I going to end up doubling this to a 4? All right, I'm going right to a 4 then. So this is a 4, this is a 6. I'm hoping that's 4 and 6. So if that's a 4, this is a 12 right here. 12. Ooh, this thing's uglier than sin. So if that's a 12, this is a 10. And how many oxygen do we have here? This is 36 total, 24. This must be a 6, huh? Is that right? Somebody got this balance with a 6 here? Yep. Okay. Ooh, that is ugly balancing. What mass of nitrogen gas? We're given the moles. And this ratio for nitrogen here is 6/4, yes? 6/4 or 1.5 times that is going to be 0.450. 0.450? That's moles. And then we have to go 1 mole of nitrogen to grams of nitrogen. Okay, so that's 36. Just ugly to balance. That's ugly. 48. All right, so 48. Which of the following is written correctly? Let's see here. All right, if I take this first one, A, and you got to look at all of these. And if I look at A, I would have PB, and then I have cyanide. CN, I have 4 cyanides. What's the charge of cyanides? Every one of these cyanides is a -1, -1, -1, -1. That means this could be a lead-4 cyanide. Do we have a lead-4? Is lead-4 valid? Do we have a pink sheet of lead-4? And do I have lead here as lead-4? And if I zoom in on this, lead can be a 2 or a 4. So I'm liking this one already. So this looks good. B is probably garbage because you have SN and you have NO2, NO2, NO2. And these NO2s are nitrites. And those nitrites are -1s. That means we have tin 3. And if I look up tin here, tin is a 2 or a 4, so that doesn't work, right? Remember, you always know what the negative is. So we know this doesn't work. So for letter C, you have AU3S. This S has to be negative. This would be sulfide -2. Well, if that's -2, this is not going to work because gold is usually well, it is 1 or a 3. So this just can't work. Letter D, you have NH4, NH4, PO4. PO4 is phosphate, which is -3. Ammonium is +1. So that doesn't equal out to be 0. In letter E, we have CR, CN, 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 CN. These cyanides, -1, -1, -1, -1. That total is -5. Right? Chromium would have to be a +5. If we look, chromium can be 2, 3, 6, can't be a 5. So that's. So the only one that works, this works as lead-4 cyanide. Okay. Let's close the book on that, baby. What I'd like to do is I want to go back to this table that we are here. And I want to show you where ours breaks down. So, and I'm going to have to zoom in on this. So our electron configuration notation is on this table as 4s2 3d1, 4s2 3d2. That's all working good so far. This is what we would expect. 4s2 3d3, but look at chromium. 4s1 3d5 instead of 4s2 3d4. Same way right here. Molybdenum 5s1 4d5. Tungsten does not do that. Go figure. Just when you think you can figure out an electron, you can never trust an electron. But those are different. So let's highlight that for these two, because we can explain these two. So highlight these two right here. Then where does it break down again? Where does it break down again? We're cruising across here. Nickel. We have 4s2 3d8. Looking good. Look at copper. 4s1 3d10. Look at silver. Instead of 4s2 3d9, it's 4s1 3d10. This one here, instead of 5s2 4d9, it's 5s1 4d10. And gold does the same thing. So one of the electrons comes out of the S, fills up the D, right? One of the electrons comes out of the S, fills up the D. So let's make a note of this as well for these, because these will pop up once in a while. So these three right here are really S1D10. Now, why would it do it? Why would it do that? This is the key word. It is more stable that way because you end up with a filled D. That makes it more stable. One comes out of the S and you end up with a filled D. And these two over here are really, these two are S1 D5. Well, you might say, okay, more stable, but how? And it turns out that this half-filled D is really stable. 1, 2, 3, 4, 5. This is according to Hund's rule. So some of these you can kind of explain the exceptions, and some of them like, oh, how? So it turns out if you have a half-filled P, half-filled D, half-filled F, it's pretty darn stable. All the electrons are spinning the same direction. So those are some exceptions I can explain. So what we wrote down for electron configuration notation is not 100%. There are some exceptions, and if you keep glancing through the table, you will see them. Again, some we can explain, some we cannot. Okay. Let's now go where we left off, and we left off at the bottom of page 19, right? And where we really left off is we put in these periodic trends, right? We put in these periodic trends going down a group, atomic radius increases. The ionization energy, the energy needed to remove an electron, the farthest out valence electron, I should say, decreases. Electron affinity to add an electron increases. Going down a group and going across, it's the opposite. Well, here's an owl question. We have magnesium ion. What are they talking about? What magnesium ion? It would be Mg plus 2, the sodium ion, and a plus the oxide ion would be O negative 2, and the nitride ion would be N negative 3. Now, so it wants to know we want to go in order of increasing atomic radius. All right, so let's look at this a little bit. Magnesium, how many protons? 12 protons, right? So this magnesium right here has 12 positive protons. If it's got a +2 charge, how many negative electrons? How many negative electrons? 10 electrons. Sodium ion right here. How many positive protons? 11 protons, right? How many electrons? 10 electrons. Oxide. How many protons? 8 protons. How many negative electrons? Whoa, come on here. How many negative electrons? 10. Nitride, nitrogen here. 7 protons. 7 protons with a -3 charge. We've got 10 electrons here. These have the same electrons. These are isoelectronic, the same number of electrons. We're going to look at that coming up. So if you just kind of look at this, which one of these is going to pull in the electron cloud the tightest? Well, 12 protons are going to pull in 10 electrons, right? It's the same number of electrons. You've got 12 positive protons pulling on 10 electrons. It's going to pull it in tighter. Not only that, when this formed an ion, we got rid of the outer level. But if you just go and think about which positives are going to pull in the most. Well, this right here, you're going to end up with magnesium being the smallest. Then what? Then you've got 11 protons pulling on 10 electrons, sodium. Then you've got 8 protons, 10 electrons, and then the biggest one is nitride. That would be the order you would get. Now listen, this is a generalization. If I have sodium, I have 1s2, 2s2, 2p6, 3s1, right? For an electron configuration notation. For the sodium ion, I have 1s2, 2s2, 2p6. Right? I get rid of this one valence electron to form a sodium ion. Generally, this is half the size. Generally. Not locked in stone. If I take a negative ion, let's take chlorine with a 0 charge. 1s2, 2s2, 2p6, 3s2, 3p5. Just if I wrote out the electron configuration notation of chlorine, neutral chlorine atom, nothing new there, correct? Nothing new. How do I make a chloride ion? I'm just adding 1 electron here, correct? All I'm going to do is add 1 electron. So the whole thing is exactly the same. It's going to end in 3p6. This is about double in size. Generally. Just generally. You get about half the size when you make a positive ion. When you make a negative ion, it's about double in size. All right, let's go to page 21. Come on, focus. So page 21 does the electron configurations of ions. Pretty much what I just did. So let's look at this. This here is a neutral atom. No charge. Nine protons, 9 electrons. This is an atom. By definition, it's neutral, right? Protons equal electrons, 9 and 9. In order to form the ion, this now would be called fluoride, right? Fluoride. This is fluorine. What's the difference? You add in an electron. This is going to be about double in size then. Fluoride, what is the noble gas configuration? Why does it do this? It attains a noble gas configuration. How many valence electrons? 8, right? 8. It's always attaining noble gas configuration to become more stable. What is the noble gas? Neon, right? Neon. This is an atom of sulfur. Again, it is a neutral atom. It ends in 3p4. It needs to end in 3p6 to be more stable. So to make the sulfide ion, it adds 2 electrons, right? The sulfur atom adds 2 electrons. What do we get? Sulfide. What is the noble gas configuration it makes? Argon. These would be about double the size. You're making negative ions, generally double. Here's my sodium atom. This is my atom. What's it going to want to do? So when I want to give up that electron, right? This is my sodium ion. We're not changing protons. We're never changing protons to get these charged ions. We're only changing electrons. This is going to be about half the size. What's my noble gas configuration right here? It's the same as neon, right? Germanium atom. In order to get a +2 charge, it gives up these 2 electrons. It gives up those 2 electrons. Now, it probably can give up those 2 as well. So if I look at germanium, let's see, some of these work, some do not. It actually does. This book does not show it. It actually gives up the next 2 as well, because germanium is a +4. So it actually then gives up these next 2 right here for a +4. All right, here's titanium, neutral atom, 3d24s2. In order to form the titanium +2 ion, it gives up these farthest out 2 valence electrons. Iron can be +2 or +3. Here's the +2 charge. Let me show you. Three or 2, if it gets rid of 1 more electron to form iron with a +3 charge, that would be a 3d5, which I just showed you is very, very stable. It would be a half-filled D, right? So when it forms a +3 charge, we'd get rid of those 2, and 1 of those would come out of the D. And that shows us this down here. Okay. So the electron configuration notation for ions, if it's a negative charge, you have to add electron. If it's a positive charge, it lost electrons. It really lost electrons. Somebody else wanted them, right? Somebody else wanted them. Okay. Two electrons of helium have different values of ms, spin. That is, they have opposite spin orientations. So for helium, for helium, it would simply be one S2, one spinning, one's going clockwise, one's going counterclockwise. These arrows represent the orientation of the magnetic field. We say their spins are paired, and the result is that the magnetic field of one electron is canceled out by the magnetic field of the second electron with opposite spins. Elements and compounds that have unpaired electrons are attracted to a magnet. Such species are said to be paramagnetic. Substances in which all electrons are paired, with the two electrons of each pair having opposite spin, experience a slight repulsion when subject to a magnetic field. They are said to be diamagnetic. So the way to remember this is this di is a pair. So it says this I took straight out of our book. So we're sitting here, this, my 4s1 electron. So I've got a single electron here. It cannot get canceled out. The magnetic field doesn't have another electron. So this is paramagnetic. We've got pairs on everything here. Diamagnetic. This is 3d9. So that one would make this paramagnetic, right? Okay. Now, this concept here is the problem I believe we just did. This concept of isoelectronic. Same number of electrons, but a different number of protons. So how many protons do we have for these? 7. Right here. 8. 9. 11. And 12. Protons. Notice same number of electrons. And this actually has our radius on here. Ionic radius and atomic radius. The atomic radius is the neutral atom. So if you go from the neutral atom, this is more than double. This is more than double. This is more than double. This is about half, right? This is about half when you make a positive ion. So if you make a positive ion, the ionic radius is about half. These are doubled, at least doubled. All right, here's our last out example and our last page. It says this. Considering only ions with charges +1, +2, -1, -2, or neutral atoms give the symbols for 4 species that are isoelectronic with potassium. Well, first of all, how many electrons does this have? Isoelectronic, you need to know how many electrons. "19 protons, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 if it's a neutral atom, but it's a positive charge. So I'm going to get rid of that, right? So how many electrons are we talking? We're talking 18 electrons. What neutral atom has 18 electrons? What neutral atom has 18 electrons? This is my noble gas configuration, correct? What ends in 3p6? Neutral atom would be argon, right? 18 electrons for argon. So my neutral atom I can put in here is argon. 18, neutral atom, no charge. Now, what ions are going to have 18 electrons? Let's go to our periodic table. The neutral potassium atom would have 19 electrons, right? The neutral potassium atom, what is it going to want to do? Get rid of 1 electron, right? Get rid of 1 electron. So that's our example that we started with, K+, correct? What about calcium? Calcium wants to get rid of 2 electrons, correct? Calcium wants to get rid of, what is it? This right here is 1s1, 2s1, 3, 4s1, 4s2, correct? If it gets rid of the 4s2, it's going to have the same outer lobe electrons as argon. We know for sure calcium with a +2 charge has 20 protons and 18 electrons. So there is my +2. This is my neutral atom because we have to match this up. What's my -1? I've got to have 18 electrons. That's going to be chlorine, correct? Chlorine would add an electron, and my -2 would be sulfur would add 2 electrons. So I would have chlorine, chloride is my -1, and sulfide would be my -2. All right, very last question of this chapter. A monoatomic, that's a single element with a charge, ion. It has a charge of -1, has an isoelectronic configuration of 1s2, 2s2, 2p6, 3s2, 3p6. This is the ion. If this is the ion with a negative charge, -1 charge, how many electrons? 2, 4, 10, 12, 18 electrons. The ion has 18 electrons. What does it have to be? If it gained 1 electron, should be chloride, right? This is chloride. It's chlorine, which would be 3p5. It has a charge of -1. So chlorine 0 ends in 3p5. The ion ends in 3p6. What is the chemical symbol of the noble gas? This ion is isoelectronic with argon. So what is the formula? I think this must be the ion. This must be chloride in all. Is it chloride? Who's done a question like this? I've been looking for the name for chloride here, because this is the symbol. The ion, it must be chloride they want. I'll want chloride here and Cl -1 here, I think. Okay. Final, I guess we can do final quiz questions Friday morning. The quiz is due Friday night. Owl chapter 7's Friday night. Print off the next unit. Learning guide. The next unit, learning guide.